Hi everyone, I'm a member of UCI team in TrueChip Solutions. Today's webinar is about unleashing innovation with UCI. So let's move further with the introduction first. So the UCI, which is called Universal Chiplet Interconnect Express, is an open industry standard interconnect offering high bandwidth, low latency, power efficient, and cost effective on package connectivity between chiplets. It addresses the projected growing demands of compute, memory, storage, and connectivity across the entire compute continuum spanning cloud, edge, enterprise, 5G, automotive, high performance computing, and handheld segments. UCI provides the ability to package dies from different sources, including different fabs, different designs, and different packaging technologies. UCI supports variety of protocols, data rates, error detection, and correction features. UCI is also used for off-package interconnect using the UCI retimer. So the UCI module, it allows three different packaging options that are standard package, advanced package, and UCI 3D, and it covers the spectrum from lowest cost to best performance interconnects. So the first package, which is standard package, so this packaging technology is used for low cost and long reach, and also it interconnects using traces on organic package or substrate while using providing significantly better bit error rate characteristics compared to off-package certs. So the second package, which is called advanced package, and this packaging technology is used for performance optimized applications. Consequently, the channel reach is short and the interconnect is expected to be optimized for high bandwidth and low latency with best performance and power efficient characteristics. So here are some examples of advanced package interfaces. So there is UCI 3D, which is enhanced in UCI 2.0. So this packaging technology uses a two-dimensional array of interconnect bumps for data transmission between dies, where one die is stacked on top of another die. A menu of design options are provided for vendors to develop standard building blocks. So here are the UCI configuration. So this one is the single module configuration for the standard package, which supports the lane width as cross 16 or cross 8, and the second one is for advanced package, a single module configuration that supports lane width for cross 64 or cross 32. And UCI also supports multi-module configuration for both the standard and advanced package, where the PHY can be instantiated as 2 or 4. So this is the enhanced feature, which is the sideband only configuration. So here we can see that this sideband interface can be instantiated as 1, 2 or 4 for the single PHY logic. So let's have a look on the UCI components. So there are the three components for the UCI. The first one is protocol layer, die-to-die adapter layer, and the last one is physical layer. So the protocol layer that maps PCI and CXL as well as any streaming protocol, and the Flit transfer and optimization. And the adapter layer provides a low latency optimized data path for protocol flits, and physical layer that has two types of connections. The first one is sideband, that is used for parameter exchanges, register accesses for debug compliance, and coordination with the remote partner for link training and management. And each module has its own set of sideband signal. And the second connection, which is main band, and it is the main data path of UCI. So let's have a look on another interfaces, that are row die-to-die interface that lies between physical layer and the adapter layer. The second one is Flit aware die-to-die interface that lies between die-to-die adapter and the protocol layer. So let's have a brief about these UCI components. So the first one is protocol layer, that is responsible for generating all type of Flit formats and the protocol related features are kept separate from Flit formats and packetization. It also transfers the Flits to the adapter layer after the completion of FDI bring up. And there are some operating formats that are supported by the protocol layer. So here are some formats that are supported for PCI format. So also there are some operating formats that are supported for streaming protocol and the below formats that are supported for CXL Flit mode. And there is one more protocol that is enhanced in UCIe 2.0, which is called Management Transport Protocol, for which the protocol's row mode, standard 256 byte start header and end header Flit formats are supported. So let's have a look on the protocol mapping. So here, this is the mapping of Flit formats for the different Flit modes. So where we can see this is the enhanced managed transport protocol. So we can see that for this protocol, these Flit formats are supported or these are also optional. But but 68 byte format is not supported for the management transport protocol. The second component, which is adapter layer, that do the handshaking with physical layer called RDI bring up and with the protocol layer that is called FDI bring up. And it also finalizes the protocol supported for the transmission through the protocol and by exchanging parameters with its remote link partner, which is the another adapter layer. And the adapter layer supports some features that are functionalities, Flit format details, CRC competition, retry mechanism, arbitration and muxing, parameter negotiation, link state management, and multiple stacks with enhanced multi-protocol enable negotiation. And it also supports some capability negotiation between link partner and remote link partner for these different Flit formats. So let's have a look on the functionalities that are performed in die-to-die adapter. As we can see, these two interfaces, FDI and RDI, that adapter layer communicates using these interfaces to the another layers. Like FDI, adapter layer uses FDI interface to connect with the protocol layer, and it uses RDI interface to communicate with the physical layer. And adapter layer supports these features. So these are the formats that are supported by the UCI and the formats that are enhanced by the adapter layer. So the first format, which is raw format, and this format is mandatory for streaming protocol and optional for other protocols, and retry is also not required for this particular raw format. The second format, which is 68 byte Flit format, and it is mandatory for CXL 68 byte Flit mode protocol or PCI non-Flit mode, and it's optional for streaming protocols. And the retry is also performed over this Flit. When the transmitting adapter has no Flits to send, it terminates the data stream with a pose of data stream, which is called PDS token, and is a variable size Flit that carries a 2 byte spatial Flit header. So let's have a look on the formats of the 68 byte. So here we can see each 68 byte Flit format has 2 bytes of Flit header and 2 bytes of CRC. And if there is no format to send after a Flit format, so we can say that the 2 bytes of PDS header will be added to that format. So this is the Flit header for format 2 and it's without retry. So we can see these 2 bytes are of the Flit header which has different fields. And similarly the Flit header for format 2 with retry. So this is the format 3, which is named as standard 256 byte end header Flit format, and this particular format is for PCI, and this mode is mandatory for PCI and optional for streaming protocols. Now the DLP0 and DLP1 are replaced with the Flit header for UCI and are driven by the UCI adapter. So we can see here these are the 6 DLP bytes where the 0th and first DLP bytes are replaced with the Flit header bytes. Now, the FDI provides a separate interface for DLLP transfer from the protocol layer to the adapter layer. So, similarly, the standard 256-byte end header Flit format also supported for streaming protocols, and there's one more protocol which is enhanced in UCIe 2.0, which is called Management Transport Protocol. So the format 4, which is called standard 256-byte start header Flit format, which is supported for CXL 256-byte Flit mode, and it's optional for streaming protocol and Flit modes, PCI Flit modes. So, standard 256-byte start header Flit format for the management transport protocol, which is enhanced in UCIe 2.0, and MTP is the message used for management related functionality on a management network in UCI based chiplets. So here is the Flit format for this particular format, which is called management transport protocol. So let's have a look on the Flit header for these different formats, which are format 3, format 4, format 5 and format 6 without retry, where these 2 bytes are Flit header bytes and that are containing different fields. Similarly, this Flit header is for these different formats with retry. So the next format, which is called latency optimized 256-byte Flit mode, and this is for without optional bytes, and it is supported for CXL.io. Now the same protocol, which is also supported for CXL cache mem and streaming protocol with a different format. And similarly, this format is also supported for management transport protocol. Now, the another format, which is called latency optimized 256-byte with optional bytes Flit format, which is supported for CXL IO or PCI. So, and also it is also recommended for to support for the streaming protocol. Now, the same protocol is also supported for the CXL cache mem with a different format. Similarly, this format is also supported for streaming protocol. Now, one another protocol which is enhanced in UCIe 2.0 and that contains a different format for management transport protocol. Now, let's have a look on the CRC computation, which is also called cyclic redundant checks, which is of 16 bits that is computed over 128 bytes of the message, or we can say for each 256 byte of packet, there will be 4 bytes of CRC that will be added by the adapter layer. Now, this is the retry mechanism of UCI, which is a simplified version of retry mechanism of PCI. So there are some features of the retry where selective NAC and associated rules are not applicable for UCI. All 10-bit PCI retry related counters are replaced with 8-bit counters in UCI. There is a replay timeout Flit count, which is a 9-bit counter. A NAC withdrawal allowed is always set to 0-bit. And the idle Flit handshake phase is not applicable for UCI, and the sequence number handshake phase and normal Flit exchange phase is applicable for UCI. Now, let's have a look on the arbitration in muxing. So here we can say that the adapter layer performs the arbitration or stack multiplexing for different formats, like for the single format and for the multi protocols also. Let's suppose there we have a single stack of CXL, and CXL supports two protocols, which is IO and cache mem, and for both of the protocols there will be different FDI interface. Similarly, if the UCI has multiple stacks and both the stacks are of CXL, then there will be 4 protocols, each 2 protocol containing in single stack. Then we can say that there will be 4 FDI interfaces that will be supported for different protocols. Now we can see the 2 stacks multiplexed with enhanced multi-protocol enable negotiated, or here we can say that if 2 stacks are supported and both could be of different protocols. So let's have a look on some different protocols that can be supported by both the stacks. So here are some examples we can say, or some scenarios we can see where stack 0 and stack 1 are of different protocols. So the third layer, which is called physical layer, that too the handshaking with the adapter layer, which is called RDI bring up after completion of training with its remote link partner, that is the physical layer of another die. Logic 5 implements the link initialization, training and calibration algorithms and test and repair functionality. So it supports some features that are like it supports data rates up to 4, 8, 12, 16, 24 and 32 GT per second. And it also supports for advanced and standard package interconnects. Support for clock and power gating mechanism. And the physical layer supports valid framing, link initialization and training, UCI package module, retimer. So let's start with the valid framing for the physical layer. So the valid signal is used to frame the transmitted data. For each 8-bit data packet, the valid is asserted for the first 4 UI, or we can say that the valid is asserted for the 2 clock cycles and will be de-asserted for the next 2 clock cycles. Mainband clock is set to the slowest input-output data rate, which is 2 GHz for 4 GT per second. The sideband initialization procedure is performed at 800 mega transfer per second with 800 MHz sideband clock. Have a look on the UCI module. The UCI physical interface consists of building blocks called modules. There are two types of module. First is the advanced package module, which consists of data, clock, valid, track lanes for the main band and data, clock lanes for the sideband. Similarly, the second module is standard package module, which consists of data, clock, valid and track lanes for the main band and data and clock lanes for the sideband. Now let's go through the retimer. The retimer is used for Flit transfer across the off-package interconnect, resolution of link and protocol parameters with remote retimer partner to ensure interoperability between UCI dies end to end. So we can see here in the block diagram the first the package 0 and package 1 that are connected through the off-package interconnect. So here is the UCI link initialization, which covers some steps like sideband initialization, training parameter exchanges on sideband, mainband training and protocol parameter exchanges on sideband. And lastly, the Flit transfer can begin after the completion of the stage 3rd. So here is the physical layer link training, where these are the states. The first state, which is reset, then SB init, MB init, MB train, link init, and after the physical layer moving to active state, it can also go through the phi retrain, and this is the train error state where the phi layer can go through the any state, and two more states that are L1 and L2. Now let's have a brief about these states. So the first state, which is reset, so physical layer must remain in reset for a minimum of 4 milliseconds upon every entry to reset. The second state, which is SB init, so the SB init initialization procedure is performed at 800 mega transfer per second with 800 megahertz sideband clock. Sideband initialization state, where the sideband is detected, repaired and out of reset messages transmitted. Mainband, so the next one is ambient state, so where the mainband clock is set to the slowest input output data rate, which is 2 GHz for 4 GT per second, and following sideband initialization, mainband is initialized at the lowest speed, and the both dies perform on die calibration followed by interconnect repair. Now let's have a look on the substates of the mainband initialization. So these are the substates for the mainband initialization. Now there is an enhancement in UCIe 2.0, which is a feature in MB-init state. So there is a state which is MB-init param state, which is having MB-init stall mechanism, which is used for additional init time to follow phase 1. Or we can see here in the diagram that the phi layer, when goes through the ambinit param to the train error, then it moves to the reset, that is called the phase 1. And the phase 1 is also called management transport path. Now moving further, the next state is ambitrain state. So the main band speed of operation is set to the highest negotiated data rate. Die-to-die training of main band is performed to center the clock with respect to data. And here we can see these are the substates of the ambitrain state. Now let's have a look on this each state of main band training. One of these basic operation is performed. So the first one is transmitter initiated data to clock point test. Another one is transmitter initiated data to clock I width sweep. And the next one is receiver initiated data to clock point test. And the last one is receiver initiated data to clock I width sweep. Now let's moving further with the link init state, which is used to exchange adapter and link management messages, and this state also performs RDI and FDI bring up. Now the active state, which is the state in which transactions are sent and received. L1 and L2 state, which are the power management states. Phi retrain state, which is used to begin the retrain flow for the link during runtime. And the train error state, which is entered when a fatal or non-fatal event occurs at any point during link training or operation. Now let's have a look on the sideband, which is to provide a out-of-band channel for link training. It also provides interface for sideband access of registers of the link partner. And it is also used for link management packets and parameter exchanges with remote link partner. And adapter forwards a remote die sideband access over RDI to the physical layer. The physical layer is also responsible for framing and transporting sideband packets over the UCI link. And the sideband packets include register access requests, completions, or messages. Now let's have a look on the sideband packet transmission. So in the above figure, we can see that the data is transmitting with the 64 UI high and 32 UI low. So a single message packet will be transmitting with the complete packet of the 64 UI high and 32 UI low. Now in UCIe 2.0, there is an enhancement which is called sideband performant mode packet transmission, where we can say that the data will be transmitting, the sideband message will be transmitting without 32 UI low. So, or we can say that the data or the sideband message will be continuously transmitting with the 64 UI. Now let's have a look on the sideband packet types. So there are different categories of packets that are supported in UCI, like register accesses, messages without data, and messages with data. Now every packet carries a 5-bit opcode, 3-bit source identifier, and a 3-bit destination identifier. The 5-bit opcode indicates the packet type as well as whether it carries 32-bit of data or 64-bit of data. So this is the packet description. So we can see that there are the opcode encodings, there are the source IDs and destination ID for FDI, and these are the source and destination encodings on RDI, and here is the source ID and destination ID for UCI link. So these are the registered access packets. So the above one is for the registered access request and the below one registered access completions. Now we have the sideband message formats for with data and without data. So the upper one we can see which the packet is without data, and for the lower packet we can see that this complete packet is with data. So moving further, let's have a look on the RDI bringer flow. So the after completion of physical layer link training, RDI bring up starts, and RDI bring up is handshaking between physical layer and the adapter layer. The removal of clock gating is performed during RDI bring up. Now this is the RDI bring up flow, where we can say that the RDI bring up flow takes place between phi layer and adapter layer, and after the completion of RDI bring up, the adapter can start the parameter negotiation. So this is the RDI state machine, where these are the states for the RDI FSM. So we can see there is active state, retrain state, L1 state, L2 state, link error state, disabled state, and link reset state. So let's have a look on the waveform for the RDI bring up. So here we can see that there is a signal PL clock request that will be asserted by the physical layer to start the RDI bring up. And we can see there is this signal which is called LP state request. So whenever the adapter will be asserting this signal, or whenever adapter will be requesting for the active state, the physical layer will be sending the status of active state. So after the completion of RDI bring up, the parameter exchange starts. So here we can see that this parameter exchange is for PCI or CXL, where both the adapter layer exchanges their capabilities. So this is the parameter exchange for the multi-stack. So we can see this parameter negotiation is for where both the stacks are CXL or both the stacks are PCI. Here we can see that the stack 0 is PCI and stack 1 is streaming. Then the parameter negotiation will be happening in this form. Now we can see the stack 0 is streaming and stack 1 is PCI, and if both stacks are streaming, then the messages will be transmitting this way. And if stack 0 is streaming and stack 1 is CXL, then adapter to adapter communication will be happening this way. Now let's move to FDI bringer flow, which happens between the adapter layer and protocol layer. So after the completion of parameter exchange between the link partner, FDI bring up starts, and removal of clock gating is performed during FDI bring up. After the completion of FDI bring up, protocol layer starts transmitting the flits. So here we can see that the FDI bring up flow is there. So after the completion of FDI bring up or FDI state moving to active state, the protocol layer will start transmitting the flits. So here is the FDI state machine, where these are the states for this state machine. So this is the waveform for the FDI bring up, where we can similarly see as the RDI bring up. Whenever the protocol will be requesting for the state, active state, the adapter layer will change the state to the active. So let's have a look on the system architecture, which is an enhancement in UCIe 2.0. So while creating an ecosystem by the help of UCI between the chiplets, UCI supports complete system architecture for the multiple chiplets connectivity. So for that we have 3 points here. So the first one is UCI manageability. So it is an optional or defines mechanism to manage a UCI based system in package that is independent of UCI mainband protocols. The second one, which is management transport packet encapsulation. In this architecture, a management port gateway is an entity that provides the bridging functionality when transporting an MTP from a local SOC management fabric or from a UCI link. This section deals with the how MTPs are sent or received over UCI sideband or mainband links through the process of encapsulation. So the management port messages is used to refer to all the sideband and mainband messages that relate to encapsulation. So the third one, which is UCI debug and test architecture. So UCI debug and test architecture provides a standardized test and debug infrastructure for UCI based chiplets and system in packages to enable standard test and debug methods in a UCI based open chiplet ecosystem. Now let's have a brief about the UCI manageability. So a UCI based system in package that supports manageability contains one or more UCI chiplets that support UCI manageability. So as we can also see in this diagram, all the chiplets that are supported main management port, and the connections of the chiplets are done by the management ports, and also the data transmission will be supported by the management transport protocol. So the manageability capabilities are discoverable and configurable, allowing a common firmware base to be rapidly used across system and packages. If the management domain contains more than one chiplet, then the chiplets are interconnected. as we can see in the diagram 2. UCI management transport packets are produced and consumed by management entities on the management network, and the packets flow unmodified through the network. Now moving forward, let's have a brief about the management transport packet encapsulation. So all the management ports in a chiplet must support encapsulation. Chiplet support for management port on a UCI sideband link or a UCI mainband link are independently optional. When management port is supported on a UCI link, or we can say whether it is sideband or mainband, the management path on the link is set up. After that, the encapsulated MTPs can be sent and received. Here we can see in the diagram of UCI sideband management path. So we can say that the management transport packet encapsulation is a technique to transmit the management transport packet through the different layers of the UCI. So moving further, management port messages is used to refer to all the mainband and sideband messages. Now the MTPs are transported between management port gateways on each end of the UCI link using either the sideband or whether the mainband path. Now let's have a brief about the UCI debug and test architecture, where it is architected on top of the UCI manageability infrastructure and uses the architectural elements of that infrastructure for chiplet level or system and package level testing and debug. So here is the DMH, which is called DFX Management Hub, that provides appropriate routing of manageability packets that target various POCs under it. While the ATE interfaces covered above are the UCI sideband or mainband, there are some other interfaces also possible for the connection, that are JTAG, GPIO and PCI. And there is at least one debug port pinned out in the package for SIP level debugging. The port could be any of JTAG, GPIO, PCI, USB, SMBus or I2C or I3C. So we can say that UCI debug and test architecture is used for the single chiplet testing, multiple chiplet or system and package level testing and overall system level testing. So here we have example for the UCI based testing of chiplets in a system and package. So now the TrueChip VIP transaction logs and waveforms. So like after the completion of FDI bring-up, protocol layer starts transmitting the flits. TrueChip's transaction logs and waveforms of the various flit formats. So let's have a look on these formats and transaction logs. So these are the raw format transaction log, the waveform for the raw format. Now we have the transaction log and waveform for the 68-byte flit format. Now we have the transaction log and waveform for standard 256-byte flit mode for PCI 6. And these are the transaction log and waveform for standard 256-byte flit mode for CXL cacheman. Now we have the transaction log and waveform for standard 256-byte flit mode for CXL IO. And we have the waveform and transaction log for latency optimized 256-byte flit mode for CXL IO. Now these are the transaction log and waveform for latency optimized 256-byte flit mode for CXL cache. Now let's have a look on the benefits and requirements. So mappings for all protocols are done using a flit format, including the raw format. So three different packaging options are, that are standard package, advanced package and UCI 3D. Where we can see for the UCI 3D, which is used for the higher bandwidth and lower power as compared to 2D and 2.5D architectures, and the channel reach is 3D vertical. To increase bandwidth, support for the multi-module and ensures interoperability and keeps latency down. It enables repairs through the redundant lanes. A UCI retimer may be used to extend the UCI connectivity beyond the package using an off-package interconnect. There are two additional requirements for ensuring success in your UCI based multi-die system that it ensures interconnects perform as expected through set testing. It employ a silicon lifecycle management strategies. Thank you.